It is the sum of the individual potentials added together to give the total net potential at a particular point. The potential due to a system of charges can be found using the formula V is equal to V1 plus V2 plus V3 etc. up to Vn. From infinity to those particular points in space, those work done will attribute or will combine to form what is the net potential energy of that particular system. To assemble this particular system, which means that already there is an energy here and we are going to add even more energy to that system. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were discussing about potentials and capacitance. Let us start with the potential due to a system of charges. As we all know, if there is a point P, let's say this is the point P, and there are charges Q1, Q2 and Q3 at distance R away from that particular point P, what will be the effective potential at point P? So let's say that the distance the first distance which is from P to Q1 is denoted by R1P, and the distance from P to Q2 is denoted by R2P, and the distance from P to Q3 is denoted by R3P. Then we have our parameters which states that there is a charge, there is a distance, and what we have to find is the potential at that particular point. And for that, we already know that the net potential will be equal to, that is V net will be equal to the total sum of, or the total vector sum of the individual potentials at particular points. That is, it will be the potential due to Q1, Q2 and Q3 added together. That is, we can write it as V1 plus V2 plus V3, and if there is n number of charges, this will continue up to Vn. So we can just say that it is the sum of the individual potentials added together to give the total net potential at a particular point. In this particular case, we can say that the net potential experienced by point P is due to the individual potentials given by Q1, Q2, Q3 added together due to the principle of superposition. So we can actually say that we can find the net potential by expanding the equation, because we already know that V is equal to KQ divided by R. So we already have a Q here, which is nothing but Q1, Q2, Q3. And we already have R, which is indicated by R1P, R2P and R3P. For V1, we can write it as KQ1 divided by R1P plus KQ2 divided by R2P, and for KQ3 divided by R3P. So the common factor will take it outside, that is K. K is nothing but 1 by 4 pi epsilon naught, and the remaining we'll write it inside the bracket Q1 by R1P plus Q2 by R2P plus Q3 by R3P. Like this, the potential or the net potential, the total potential can be found out in a particular point. This is actually very similar to the properties we have already seen before, that is the force due to a system of charges, potential energy due to a system of charges, and so on, electric field due to a system of charges, so forth. So for a system of, the potential due to a system of charges can be found using the formula V is equal to V1 plus V2 plus V3 etc. up to Vn. For this particular example, we are taking the case of a 3 charged quantities, or simply we can say that for a system consisting of 3 charges at point P, the potential will be given by V1 plus V2 plus V3. So the essential point you have to take into your mind is that it is the individual potentials added together to give the potential at point P. So I hope this is clear. We were discussing about electric field and potential energy and everything. So we are seeing it as individual quantities. So is there any relation between them? Can we correlate them in any way possible? And how can we form an equation or a principle so that it suggests both are interlinked. So we are going to find out what is the relation between electric field and potential. So first, in order to find that, we are going to consider a situation and we are going to draw up some figures. So imagine that there are two surfaces like this. Imagine that there are two surfaces. Let's say this is surface A and this is surface B. Then the distance between the two surfaces is given by a small distance, which is dr. Now we can practically say that there are two surfaces and the two surfaces are separated by a distance of dr. And the next consideration we are going to take is that the electric field in this particular case is in this direction. So the electric field is in the direction perpendicular to the planes we have taken. Why we are taking electric fields? Because we are trying to prove the relation between potential and electric field. So we have to take electric field. We have to consider electric field. And now potential. So we know that there is a potential at point B and there is a potential at point A. So what are those potentials? So let's say that at point A, potential is equal to V1, or let's say it is VA, and potential at B, V at B is equal to VB. So we have the two potentials, which is VA and VB. But which one is stronger, which one is weaker? How do you know that? We remember the properties of potential, which was recited in the last class, which clearly explains that potential decreases along the line of the field. The property clearly stated that as we move along the electric field, the potential decreases, which means that potential at point B is comparatively higher than the potential at point A. So we can effectively write VA as V minus, let's say, dV, a small charge. So we can say that the potential at point A will be dV times, that is a small amount of potential difference will be existing there, and that is denoted by V minus dV. And the potential at VB is denoted just by VB, that is one will be V and one will be V minus dV. So we can say that VB will be denoted by V. So this relation exists, that is V minus dV. Here it will be V, potential will be V, here it will be V minus dV, because there is a difference of dr distance and along the electric field the potential will decrease. Now imagine that I have brought a charge, let's say a unit positive charge I have kept here, which is denoted by Q, and Q is equal to plus 1 coulomb. I'm taking it as plus 1 coulomb so that the calculations are easier. So basically it is a unit test charge so that we can prove the relation between potential and the electric field. In order to prove that, I'm taking a small charge which is plus Q, that is 1 coulomb, and I'm going to move it from the potential A to potential B. So from point A to point B, I'm going to move this charge from point A to point B along this line, and since I'm moving it, I have to do work. And one more thing is that since it is a positive charge moving against the electric field, which always means that I have to do work, because the electric field will be in this direction, which means that the force experienced by this particular point charge will also be in the direction of the force. Simply because if there is a positive charge and another positive charge, then it will be repelled. The force experienced will be in the direction of the electric field, and this is the direction of the electric field, which means that this particular charge will be experiencing a force in the direction of the electric field because both are positive charge. So a force will be experienced, and the force experienced will be equal to QE. So will be equal to QE because Q is the charge and E is the electric field. Since Q is 1, we can just say that the magnitude of the electric field is the force experienced at that particular point. So I have to do a work in order to move this particular charge from point A to point B. That work is denoted by WAB. That is, I am doing a work in moving a charge from point A to point B. That work is denoted as WAB. One more thing to remember from the previous topics we have discussed is that work done is stored as potential energy, but we are discussing in terms of potential only. So not potential energy, just electrostatic potential. So work experienced by unit charge. The work done in bringing a unit charge from infinity to a particular point is defined as potential. So that is given by this equation. So in this particular case, we can say that the work done, that is WAB, will be equal to, let's say this is Q, that particular Q which is here, and that is just nothing but 1 coulomb. So that WAB is equal to potential difference at this point, that is V minus, let's say it is VB minus VA. So this will be the work done in bringing the unit positive charge from point A to point B. So we can actually write this as WAB divided by Q will be equal to VB is nothing but V and VA is nothing but V minus dV. So if we open the bracket, minus sign will go in, minus V plus dV. So the V's will get cancelled each other and there will be only plus dV. So we can actually say that WAB will be equal to dV. That is the small difference. This small difference will be the potential difference between those 2 points, and that will be equal to the work done in moving a point charge from point A to point B. Now we are not just done yet, because we already know the equation for work. Here in this particular point, we already know an equation for work that is given by force times displacement and the cos of the angle between the force and displacement. And we know that work done here is from point A to point B, which means that work is nothing but F dot dr divided by Q. Why F dot dr? Because it is traveling a distance of small dr. This is the distance it is traveling, so we can say that the distance traveled is just dr. So F dot dr, the force experienced dot dr divided by Q, that is the work given, will be equal to dV. Now we can also say that F dot dr is F dr cos theta. F dr cos theta. F dr cos theta is equal to dV. Now one more consideration is that cos theta here is just 180 degrees, because compared to the position of the electric field, the force, everything. So let's say the force applied is in the direction of the electric field. Compared to that force, the displacement is occurring 180 degrees anti-parallel to that. So we can say that the displacement is at an angle of 180 degrees, which means that cos 180. So we all know that cos 180 degrees is nothing but minus 1. Cos 180 degrees is nothing but minus 1. So we can write it as minus F dr by Q is equal to dV. Now we have to remember one more equation that states that F by Q is equal to E. Why? We already know that F is equal to QE. The force experienced will be equal to magnitude of the charge and magnitude of the electric field experienced at that particular point. So we can rewrite this equation into this form, bringing the Q down, that is F by Q is equal to E. Now we have an F here and a Q downstairs, so we can write it as minus EdR is equal to dV, or we can simply write E is equal to minus dV by dr. So this is how we find a relation between the electric field and potential. That is, electric field is the negative gradient of potential. So we can write it as E is equal to minus dV by dr. So what we did actually was we considered two surfaces which was at a point A and point B. And we considered an electric field passing through that surface. Depending on that electric field, here I have taken it in this direction. So that means that point B will have a higher potential compared to point A, because the property clearly states that potential decreases along the direction of the field. And I have placed a point charge Q, let's say point A, and that will experience a force which is in the direction of the electric field, and that force is given by QE. Anyways, so if I have to move this particular charge from point A to point B, I have to do work. This work is stored as potential energy, or we can just say that work divided by charge, or work done per unit charge, or work done per charge, is nothing but the potential. And here the potential is the potential difference, that is V minus dV. So VB minus VA. Expanding that, we'll get this. So we can write it as work done per charge will be equal to dV, because that is the only quantity remaining. And we are not stopping there. We are introducing or substituting an equation for work done, which is nothing but F dot dr. Cos theta gets eliminated because the angle between force and displacement is 180 degrees, which means that cos theta will be minus 1. So we can write it as minus F dr is equal to dV. And we know that F by Q is nothing but E, or the electric field given by the previous equations from previous topics. So we can conclude that minus E dr is equal to dV. Rearranging that equation in terms of electric field, I can write it as E is equal to minus dV by dr. Or we can say that electric field is the negative gradient of potential. That is the relationship between electric field and potential. As electric field increases, potential actually decreases. So this is a very important question. This has been asked a couple of times in your exam. So please pay attention to this. This is an easy derivation which you can do in like 2 minutes. So please study about that. All you need is two surfaces and one point charge, and you only need to understand the equation for work, electric field, and how to convert the equation. Since we were discussing about potential only, potential energy has been feeling very sad, and we have to find out what is the potential energy due to a system of charges. Just like we found out what was the potential due to a system of charges, what was the electric field due to a system of charges, we are going to find out what is the potential energy due to a system of charges. For that, again, we are going to consider a random situation in space. Let's say there is a space where nothing is existing. It is the vacuum of space. And from there, I'm going to bring a point charge to a particular point. Let's say from infinity. So what I'm going to do is, from infinite distance away, I'm going to bring a charge to a particular point. So I'm going to bring Q1 from infinite distance away to a particular point in space. And for that, I have to do W1 work. But since nothing is existing there, no force is required to move that particular charge from infinity to that particular point, which means that W1 will be equal to 0. That just clearly states that for bringing the first charge from infinity to a particular point, I do not have to do any work. So that is Q1. But that is not enough. I need a system of charges, which means that I have to bring another charge from infinity to that particular point. And that particular point I am choosing right here, which means that the distance between these 2 points is, let's say, R12. So I am going to bring a charge again from infinity to this particular point. So this is Q2, which means that I am bringing another charge from infinity to that particular point. But this time, will it be the same as W1? No, because at first there was no charge or no field or no force there to repel or pose any difficulties in bringing the charge Q1. But this particular case, when I'm bringing Q2, there is already a charge existing here which can pose a force against this Q2, which means that, let's say that this is a unit positive charge, then let's say all these are positive charges, then I have to say that there will be an electric field around this charge, which means that I have to do work in order to bring that charge from infinity to that particular point. If you recall the first topic I took for the second chapter, it was about bringing that unit positive charge from infinity to that particular point, and I had to do work for that. So that particular work is W2. And W2 is actually real and I have to do work, and that work is given by W2 is equal to Q2V. Now where did I get Q2V? That is because work done per charge is denoted by V, that is potential, and here I can say that the work done is W2 to bring the second charge from infinity to that particular point. So this is W2 and this is the second charge I'm bringing. Work done per charge. Work done is the second work and the work done per charge is the second charge. So work done per second charge will give you the potential V. But that potential is due to Q1. There is a charge Q1 there, which means that around this charge there will be a potential due to that particular charge, and since that charge is Q1, that potential experience will be V1. So let's say this is V1, so I'll rearrange this and I can say that W2 is equal to Q2 V1. So we are going to expand this also, because we already know there is an equation to find out the potential at any given point, and that is given by V is equal to KQ divided by R. So here the charge is Q, the potential of the particular charge is due to Q1. So this is Q1, V1, and the distance is R12. So, and remember, K is always 1 by 4 pi epsilon naught. Never ever forget about this quantity. We are writing about K in order to simplify the equation so that it doesn't appear too big. But that particular quantity, that is 1 by 4 pi epsilon naught, should always be inside your brain. Anyways, so V1 is equal to KQ1 divided by R12. We're going to substitute this equation into this equation, which means that I can write W2 is equal to Q2 into KQ1 divided by R12. So this is the work done in bringing that particular charge from infinity to that point where Q2 is now situated. Now why did I find this particular work? Because I was talking about potential energy. Then why did I find work? If you remember the first topic precisely, then you would know that the potential energy we are seeking is stored as the work done in bringing that particular charge from infinity to that particular point, which means that W is stored as U. That is, W is work done, and that is equal to the potential energy stored. So we can say that that particular W2, that is W2 will be equal to U will be equal to KQ1 Q2 divided by R. And this was already found during the discussion of first topic in the second chapter, and we have discovered it yet again for a system of two charges. That is, if there is Q1 and Q2, Q1 being brought from infinity to that particular point and Q2 being brought from infinity to that particular point, then we can say that the net work is, or the total work is equal to the total potential energy of that particular point, which is given by W1 plus W2. And W1 is nothing but 0. So we can say that it is 0 plus K Q1 Q2 divided by R, and that is the potential energy due to a system of two charges. This is due to a system of two charges. And this is only about a system of two charges. What if I want three charges? Because your textbook discusses three charges, you have to learn three charges. What if there is another charge, a stowaway charge just coming from infinity to that particular point? What about then? Then we will discuss the possibility of bringing a unit charge from infinity to a particular point again. That means from infinity, I am going to bring another charge, that is Q3, to that particular point, which is R23 distance away from the point charge Q2 to Q3, and let's say this distance is R13. So we have a system of three charges, Q1 and Q2 separated by a distance of R12, Q1 and Q3 separated by a distance of R13, and finally Q3 and Q2 separated by a distance of R23. So what will be the net potential energy of these three charges? Obviously it will be the net work done. So we are going to calculate W3. That is the work done in bringing the unit positive charge Q3 from infinity to that particular point. It can be unit positive charge, it can be just a positive charge, it can be a negative charge. Anyways, if we have to bring a charged particle from infinity to that particular point, that work will be stored as potential energy. And if we are considering this particular system, then the total potential energy will be equal to the net work done or the net potential energy at that particular point in space. So we can actually say that W3 is equal to, that is W3 will be equal to Q3 V dash. Let's assume that the potential at point 3, where Q3 is currently placed, let's say that the potential is V dash. And V dash is nothing but the combined potential of Q1 and Q2, which we actually found out earlier. So we can actually write it as, which is equal to Q3 into expanding V dash, that is K Q1 by R13 plus K Q2 by R23. That is, we already know that V dash is equal to V1 plus V2. The potential experienced at this particular point will be equal to the sum of potential due to Q1 and potential due to Q2, which is denoted by V1 and V2. So we can just directly write it as V1 plus V2. And expanding V1 and V2, we know that the equation is K Q1 by R13. The distance is from Q1 to Q3. That is why it is R13. R13 plus K Q2 divided by R23, because the distance is R23. Because direction is important. That is why 2, 3 and 1, 3 all are written as subscript. So anyways, here the common factor is the K. So we can actually take the K out, or we can directly write it as it is, and we can just say that we can take this Q inside and we can say that Q1 Q, that is K Q1 Q3 divided by R13 plus K Q2 Q3 divided by R23 will be the work done in bringing a unit charge or any charge from infinity to that particular third point in space. So we found out W1, W2 and W3. I'll just write it down separately so that you can understand it. So we already found out that W1 was equal to 0 since no work was required to bring unit charge from infinity to that particular point Q1, that is to bring Q1. And we are going to find out what is W2. We already found out what W2 was, which was equal to K Q1 Q2 divided by R12, which is nothing but the potential energy of a system of two charges. Now, evidently, W3 was to be found, which was equal to KQ1 Q3 divided by R13 plus KQ2 Q3 divided by R23. Now, we have to find work done, or the total work done in bringing all these three charges from infinity to that particular point, which will in turn give you the total potential energy of that particular system. That is, if we calculate the total work done in bringing the individual charges from infinity to those particular points in space, those work done will attribute or will combine to form what is the net potential energy of that particular system. And in this case, the work done was equal to W1 plus W2 plus W3. And we already know that W1, which is the work done in bringing the first positive charge to that particular point, is 0. So W1 will be equal to 0. W2 will be given by KQ1 Q2 divided by R12, which is nothing but the potential energy of a system of two particles, and that is written down first. That is KQ1 Q2 divided by R12 plus how much is the work done in bringing the third charge, or the work done in bringing the third charge to that particular point is given by the equation KQ1 Q3 divided by R13 plus KQ2 Q3 divided by R23. So this is the actual net potential energy of a system of three charges in space. So we can actually say that the potential energy of a system of three charges is given by this particular equation. So again, how do we calculate this? It is actually very simple if you break it down. So first, we are considering the possibility that when we bring Q1 from infinity to that particular point, let's say point A, the work done will be 0 because there is no force existing in that space in order to repel, attract or exert any force on that particular charged particle. And again, if we bring another charge from infinity to that particular point, let's say it is point B, then the distance between those two particles, I am taking it as R, and since particle 1 is Q1, particle 2 is Q2, distance between them is R12. So obviously, we have discussed in the first topic that if there is a system of two charges, we have to do work in order to bring the second charge from infinity to that particular point, and that work is stored as the potential energy of that particular system, and that was found using the work equation, and that is KQ1 Q2 divided by R12. And finally, if we bring a third charge into the system, we have to add the individual work done in assembling all those different charges in a given area of space. To put it down very simply, if you are bringing different charges from different places to a particular point, building a system, assembling a system, then the total potential energy of that particular system will be equal to the work you have done in bringing that particular charges from those particular points in space to that particular system. That is, if there is nothing in this space and I'm bringing a charge from infinity to that particular point, I don't have to do any work. But if I'm bringing a second charge, I have to experience or overcome the force which is offered by this particular individual charge. And if I build that system, this will always be in tension. This system will have an energy because of these two charges existing close by each other, and that energy is stored as potential energy. Already this system has an energy, and already a work was done in bringing the second charge from infinity to that particular point. So if I'm bringing another charge from another point in space to this particular system to assemble this particular system, which means that already there is an energy here, and we are going to add even more energy to that system. We are going to do even more work in bringing that charge to that particular system of two charges, which means that that work is also added and stored as the potential energy of this particular system, which means that three charges are right now here, which means all those work done in bringing the individual charges to assemble a system is stored as the potential energy of that particular system. I hope you have understood what was discussed today. So to summarize, we discussed about potential due to a system of charges, and it was shown clearly if there is a system of charges, you add the individual potentials and you will get the potential due to a system of charges. And later we discussed about what was the relation between electric field and potential, and we found out that electric field was equal to the negative of the potential gradient. dV by dr or dV by any quantity generally is known as a gradient. So we can say that the electric field is the negative potential gradient, and that is the relation. The way we found it was by considering two areas of different potentials and moving a positive charge or unit charge from point A to point B and calculating the work done. And finally, we found out what was the potential energy due to a system of charges. Here we took the example of 3 charges. If you want to take the example of 4 charges, it is very well similar. You only have to do or consider the work done in bringing the 4th charge from infinity to that particular point and add that to the initial W1, W2 and W3, and you will get the work done in bringing the 4th charge from infinity to that particular point. Add them all together and you will get the potential energy of that particular system. If you want, you can actually take the K, which is 1 by 4 pi epsilon naught, out of the equation and write it as a common factor. But this is the way you calculate all these things, and I believe that you have understood all these things discussed here today. So until next class with more physics, I'll see you again very soon. Thank you.